In this video, we're going to take a look at fluid pressure and fluid force. Before we do any examples together, I want to talk about some of the concepts and formulas that we'll use. So the first concept is that of fluid pressure, and you should be familiar with this if you've ever gone swimming or gone scuba diving or anything like that. We know that the deeper you get into the water, the more pressure you're going to feel. Same thing if you've been on an airplane. Obviously, there's pressure. That's what makes your ears pop. And so that's what we're talking about here. We're talking about fluid pressure, so the pressure of fluid. And that fluid pressure is found just by taking the weight density of the fluid, which of course varies by fluid. We're most often going to use water, which is 62.4 pounds per cubic foot. The weight density multiplied by the depth of the object. Now, the depth is where things are going to get interesting because it will depend on whether the entire object is at the same depth, which will not require calculus, or if we have an object that is at different depths. So if you think about, say, a sheet of metal that is rectangular, and it is at, say, 4 feet below the surface, that's going to be much easier to find than if I have the same sheet of metal, but now instead of horizontally, it's vertically, because this part that's at 4 feet will feel the same pressure that the entire sheet over here feels, but up here it's less pressure and down here is more pressure. So this is where calculus will come into play. So we're going to do one of these types of examples first, and then we'll take a look at a calculus example. Now, the fluid force is simply the fluid pressure that is exerted on the entire surface. So if you'll notice, fluid pressure is the force per unit of surface area, and so we're just going to take the fluid pressure and multiply it by the entire surface area to find fluid force. So again, A is going to represent the area, which might be given, or it might be found through geometric formula or integration. For our first example, we are not going to have to use calculus, and again, that is just based on the position of the object in the water. So if you remember on our last slide when we talked about what our objects would look like, I basically have a horizontal sheet of metal that is at a constant depth of 8 feet. And so the depth is not changing at all. It's the same depth the entire time, and that's why calculus isn't needed. So if you remember what our formula was, remember we're saying F, which is the fluid force, is equal to the fluid pressure, which is P, multiplied by the area. Now, fluid pressure we can call density, weight density, which is W, and times the depth, which is h. So h is sort of for the height, but if you're thinking about height of an object that's submerged, we're really thinking about the depth. And then of course A is the area of our figure. Now sometimes we're given information and sometimes we have to work it out, and in this case we actually are just given most of the information. So first of all, it's in 8 feet of water, so water we know has a weight density, W, of 62.4 pounds per cubic foot. Pounds per cubic foot. And I'm going to put all of the variables in as we go. The height, or depth, which is h, the depth, remember, is that unchanging 8 feet. These two values together represent P. And then we're going to take it times the area. Now, most of the time you're going to have to find the area, but if you'll notice on this one, they've actually given me the area of 8 square feet. So let's see if we can work this out. If I use my handy dandy calculator and multiply 62.4 times 8, that gives me 499.2. And what's the label? So you need to get used to this labeling system. If this is pounds on top and cubic feet on the bottom, and this has feet on top, essentially one of the feet on top will cancel with one of the feet on the bottom, and that's going to give me 499.2 pounds per square foot. I still have 8 square feet over here. Now again, using my calculator, 499.2 multiplied by 8 gives me 3,993.6. And then again, what is the label? The label would be that square feet in the denominator and square feet in the numerator cancel out, giving me a solution of pounds. And again, that makes sense because I'm finding fluid force, and fluid force would be measured in pounds. Now we need to look at what happens when not everything is consistent. So perhaps the depth of the object isn't consistent, or it's changing because the figure is submerged vertically. The length of our figure or width of our figure is changing, again, because instead of having a rectangle like we had before, we might have a figure that looks like this, which is a trapezoid that is being submerged. So here's where things get tricky. Obviously, the depth is changing, right? The depth is changing because this part of our figure will have a different fluid pressure than this part, which is different than this part. And so this distance is going to be h of y. It's going to be how deep is our object. And again, that's going to be changing. Then we have the area of our figure. So this is not a rectangle. Obviously, this is a trapezoid. But what we do, like we're very used to, is think about if I had a representative rectangle, how could I find the area of that representative rectangle? And so because the area, or because the figure is a rectangle, I'm using length times width as I normally would. Again, the length will change and the depth will change because, as we always do when we're dealing with integration, we think about those widths getting smaller and smaller, so more and more and more representative rectangles. And so that's where the dy comes in, is that width, and the length of y, again, will be this distance across, all the way across. So that's L of y. And then dy is just, again, the little width of that figure. And so if I stick all of that together, remembering where I came from is that F was equal to W, which I still have, and then H, which was the depth, which I still have, and then area, which I've replaced with Ly dy, and then the only thing we haven't talked about is our limits of integration, which will just be the depths of the endpoints of my figure. So looking back at my picture, from C to D, or vice versa. Let's do that backwards. From C to D. So now that we have the basics, let's take a look at how this looks at an example. For our first calculus example, I haven't given you much, and I did that on purpose so that we could work through all of the parts together, because some of these are going to be very straightforward and some will require more work. So before we get started, I am just going to copy that formula just so we have it. We know where we're trying to head here, and keep in mind that W stands for the weight density of our liquid, in this case is water. H of y represents the depth of our figure, which of course is going to be changing. L of y represents the length of our figure, which of course is changing. And dy represents the width of our figure, which of course is changing. And that's why all of the changing things are of course on the right side of the integral. So let's take a look now at our figure. We've got a semicircle with a radius of 2. So really, this is all I know. And it's impossible to do this question without giving yourself a place to start. And the place to start is placing our very pretty semicircle picture on a coordinate plane. So I'm going to choose to stick my coordinate plane right in the center of my figure and at the top of the water. Or the top of the figure, excuse me, the top of the figure. So now I want, because I put my x-axis here at the top of the figure, that's going to change or alter how I'm going to set up my question. So if that's the case, my coordinate plane would have a 0, 0, have the origin right there at the top center of my figure. This would be 2 because of the radius of 2. This would be negative 2, and this would be negative 2. So from here, now I can actually start to plug in some values. So to find the fluid force, I'm going to use the weight density of water, which is 62.4. And then I'm going to integrate from C to D, and C to D just tells us what are the two, based on the coordinate plane that I just drew, what are the lowest value and the highest value on the y-axis. So that is negative 2 to 0. So obviously this would be different if I chose to put the x-axis at the base of my figure, but you would still get the right answer. Everything would just be altered based on that coordinate plane. The depth of the water is going to be represented, and again I'm going to draw in a representative rectangle here. And so the depth of the water is represented by this distance. I should have used blue because I'm using blue for depth. So let me do that again. This distance is h of y. And h of y again is just the height or depth. Now because I chose to put my x-axis at the top of the figure, and my y value is going to be negative, I need my depth to be negative y. So my depth, h of y, is going to be equal to my negative y value. That's going to give me the depth of the water. So negative y happens here. The length, I'm using white for, and so the length would be the distance across. Now I want you to notice that the length of the rectangle is split in half by the y-axis. So if I can find this distance, I can just take it times 2 to find the entire length. And that's how I'm going to do it, is I'm going to find the x value, because if I think about this, this would just be the x value. And so I really just want to take 2 times the x value. Well, easier said than done, right? Because I don't know what the x value is. So the x value has to do with the fact that we're dealing with a semicircle. So if we can find the area of a circle, and the area of a circle, sorry, not area, the formula for the equation of a circle is x squared plus y squared equals the radius squared, and the radius is 2, so that's 4. And if I'm trying to find x, I'm trying to isolate x, so solve in terms of y, I would get x squared is equal to 4 squared, I'm sorry, this is supposed to be 2 squared. 2 squared, which is 4. So 4 minus y squared. And that means x is equal to plus or minus square root of 4 minus y squared. So that's going to give me my x value, and that's going to give me the positive x values, and then of course the negative x values. Now I don't need the negative one because I'm just going to multiply it by 2. So I'm going to take 2 times the square root of 4 minus y squared. That's going to be my length. So that goes here, 2 times the square root of 4 minus y squared, and then dy. Now this would be a real pain to integrate because I would have a lot of stuff going on. And so I'm not going to integrate it. I mean, you could. The good news is for your test, I'm really just going to be looking at, can you set it up correctly? because I know you can integrate. You could, factor out the 2 and the negative, and you could distribute the y and take the square root, and it would get really ugly and messy. Or you could just use your calculator, and that's what I'm going to have you do. So if you give me the setup, and of course I will look at the setup based on your picture, so looking at my picture, that is the setup. And then if you give me the solution, which in this case is 332.8 pounds, I guess that should be approximately equal to, that's all I will need for you on a question like this. Here's another example, and again, I wanted to go through an example where it was a little bit different than the last one. On this one, it's going to be difficult to find L of y. So in the last one, we had the formula for the equation of a circle. Here, I don't have the formula for the equation of a trapezoid, and so we're going to have to be a little bit more creative. Just like we did on our last example, though, we are going to set up our own coordinate plane. And so just like I did on the last one, I'm going to put it right in the center of the figure. The top side has a distance of 4, so this is 2. This has a length of 3, so this value is at -3. And then this value is obviously a length of 1. So if I'm looking at coordinates here, obviously the origin has the point 0, 0. This value right here has the point 2, 0, again, based on the picture that I drew. So if you drew it differently, it's going to be different for you. This has the point of -3, I'm sorry, 0, -3. And then because the whole distance here is 2, then this distance is 1. So this is going to have the point 1, -3. So those will come into play as we're working. Now we're still going to use the same formula, and I didn't specify that this is water, but we are going to use water on this one. So I'm going to recopy the formula, W from C to D of H of Y, L of Y, dy. And I'm still using water, so that's 62.4. And then based on my picture, I'm going from -3 to 0. And then just like I did on the last one, if I'm looking at the depth, because I set it below the x-axis, my depth, H of y, is going to be -y, just as it was last time. And L of y is what I need to solve for, and dy is just going to be dy. So really, the L of y is why I wanted to do this example, because this one's trickier. I need to find, just like on the last one, the length is going to be my x value. That's what I need. Or if I can find this distance, I would take it times 2. So I need the x value because that's this distance, which would give me the length. So how am I going to do that? I don't have a formula for the equation of a trapezoid. On my last one, I took the formula for the equation of a circle and I manipulated it to get x by itself. So now I have to use algebra. I know, can you imagine? I'm going to use point-slope form with this point and this point, because if I do that, I'm going to find the equation of this line, which will give me this x value that I will then take times 2. So I'm going to, hopefully you know point-slope form, y minus y1 equals m times x minus x1, where x1 and y1 is just any point on your line. So I'm going to use 2, 0 and 1, -3 as the 2 points. And so this is going to be y minus, and I'm going to choose to use 2, 0 for obvious reasons, because it has a 0 and that makes my job easier. M is the slope, so I'm going to use the slope formula. y2 minus y1 over x2 minus x1. And then this is x minus x1. This is just y, because y minus 0 is y, and I get -3 divided by -1, so that's +3 for the slope, and then x minus 2. And then again, 3x minus 6. What's my goal? My goal is to get x by itself, so now that I have the equation, I'm just going to manipulate it for x. And so I'm going to end up with y plus 6 equals 3x, and then divide by 3, so y over 3 plus 6 over 3, or 2, is equal to x. Now, that just gives me this distance, 1/2 of the distance that I need, so I'm going to take 2 of those. And so plugging that back in up here, I would have 2 times the quantity of y over 3 plus 2, or of course I could go ahead and multiply that through. Now, just like on the last example, yes, I could definitely very easily simplify this, integrate it, show all of the work. So just pay attention to the instructions. If they ask you to show all of the work, then show it. If they ask you to set it up, which is what I'm going to do on a question like this, I would need this step right here, and then I would let you use your calculator to integrate this from -3 to 0 and find 748.8 pounds. And again, I showed you back when we learned integration how to plug that into your calculator. Coming up next, we're going to review some of the basic integration rules and how to fit integrands to those rules.